Welcome to the fourth installment of Derby Test Track. How much does center of gravity, or CG, matter? We've all heard how important it is to move our car's center of gravity to the rear. But, how much does center of gravity actually affect our car's elapsed time? Let's find out. In this episode we will move the center of gravity on a specially prepared car and let the timer on our 42-foot aluminum track tell us how much faster or slower moving the center of gravity makes our car go. Let's do the math to see how much of a theoretical gain in potential energy we could be looking at. Gravitational potential energy is calculated by multiplying the mass of the object by acceleration due to gravity, multiplied by the height it can fall. So, the higher of two objects of equal weight will have more potential energy. If we have a car weighing 5 ounces, or 0.1417475 kilograms. Yes, that kilogram value seems ridiculous, but a kilogram is over 2.2 pounds. Acceleration due to gravity of 9.8 meters per second squared. With a CG 3 inches ahead of the rear axles, that's roughly in the middle of the car. When the car is placed in the starting position on our best track, we have a height difference of 1.1319 meters between the car's center of gravity at the starting gate and its center of gravity once it reaches the flat part of the track. So, in this scenario our car's potential energy would be 1.5724 joules. If we move our CG back 2¼ inches, to just 3/4 of an inch ahead of the rear axles, and that would be a huge move, we gain 1 inch in the height of our center of gravity at the starting gate. With our CG now just 3/4 of an inch ahead of the rear axles, our potential energy would be 1.6076 joules. That is a gain of 0.0352 joules, or a gain in potential energy of 2.2%. Not a tremendous energy gain for a big move in CG like 2¼ inches, but every little bit helps when the difference between winning and losing could be just a few thousandths of a second. Design of the experiment. We designed our experiment to minimize external variables and to provide information that is representative of actual race results. The objective of this experiment was to determine the effect of center of gravity on our test car's elapsed time. Experiment parameters. 1. A long wheelbase test car was constructed that allowed the placement of tungsten weights in different positions while maintaining a constant total weight of 5 ounces. 2. During runs, tape was placed over open weight pockets to minimize potential aerodynamic impact. 3. Unpolished maximum velocity nickel speed axles and unpolished maximum velocity precision wheels were used, with super lube silicone oil, 100 CST lubricant. In earlier tests, this lube had demonstrated its ability to maintain consistent elapsed times. 4. All axles were set with 0 degrees camber and 0 toe. No bent axles, not a rail rider. 5. The test car was constructed as a 3-wheeler, with a 60 thousandths lift of the right front axle. 6. The center lane of our 42-foot best track, with leveling kit and champ timer, was used for all test runs. Test runs were conducted indoors, on the same day, at 74 degrees Fahrenheit. An alignment jig was used to help ensure that the car was aligned with the track, and will spacing from body consistent from one run to the next. 7. 6 test runs were made at each center of gravity to establish an average and median elapsed time. 8. Centers of gravity were determined using Derby Dust CG tool. Note, any round object, such as a dowel, marking pen, large drill bit, etc., and a ruler work just as well. The point on which the car balances is its CG. The distance between that balance point and the rear axles is how we reference CG in this video. 1 inch ahead, 2 inches ahead, etc. Test results. So, we've calculated that there is free energy to be had by moving our CG to the rear of the car, which raises our CG higher, given the angle of the car in the starting gate. Now we'll see how those minor changes in potential energy translate into faster or slower times. Shown here are the elapsed times for each of the 6 test runs we made at the 8 different centers of gravity. The tested centers of gravity were 2, 1 3/4, 1 1/2, 1 1/4, 1 1/8, 1, 7/8, and 3/4 of an inch ahead of the rear axle. As in other videos, we are using the median ET as the basis for our comparison, since unlike the average, the median excludes both high and low data outliers. The median is literally the time in the middle of each set of runs at that CG. When we look at the median elapsed times graphically, it is clear that something unexpected is going on with the CG 3/4 of an inch ahead of rear axles. It is much slower than it should be. This unexpected result can also be seen when looking at the worst ET for each CG. So, what's going on? When moving the CG close to the rear axles, there are performance factors at play other than just increasing potential energy. The greatest of these being instability created when too much weight is taken off the front steering wheel. Assuming that the car is a 3-wheeler like our test car. This instability could be observed in our test runs, as the car wandered slightly and made 1 or 2 more contacts with the guide rail. The negative impact of that wandering and guide rail contact on elapsed times was startling. Another possibility is that the slap of the spring-loaded starting gate against the bottom of the track could be causing the lighter weight front end of the car to jump or bounce more, throwing the car out of alignment at the starting gate. A note: in the days before spring-loaded starting gates, when the starting posts were dropped relatively slowly, and Grandpa and Dad were deliberately making cars that rode up the starting gate post as it was dropped, the possibility of the car coming back down on the track out of alignment was outweighed by the instant 2-inch lead the car would have from doing the wheelie and riding up and over the starting post as it was lowered. Looking at our elapsed times for 7/8 to 2 inches ahead of the rear axles, the change in elapsed times look more like what we would expect, given the minor sacrifices in potential energy made as we move the CG forward. We still see some data anomalies, such as the median ET for 1.5 inches, due to uncontrolled variables. Theory meets the real world. We can see that moving the GC just 1/4 of an inch backwards, from 1.25 inches to 1 inch ahead of the rear axles, resulted in a median ET reduction of 8 thousandths of a second. Using again the example of the 2024 Council Tiger Cub race that was determined by just 7.5 thousandths of a second, this could be the win-loss margin. Conclusions. 1. A center of gravity of 7/8 of an inch ahead of the rear axles appears to be the limit of rearward CG before elapsed times are degraded by front-end instability. 2. Any gain in elapsed time, by moving the CG from 7/8 to 1 inch ahead of the rear axles, did not exceed background noise in data. 3. 8 thousandths of a second improvement in ET, just by moving the CG from 1.25 to 1 inch ahead of the rear axles. This could be the difference between first and second place in a close race. 4. A CG of 1 inch ahead of the rear axles is a good compromise between maximizing potential energy and risking a loss due to instability. 5. If you don't pay attention to your car's CG, you could be throwing away free energy. For us, there are many similarities between Pinewood Derby and our go-kart racing experience. Driving skills aside, in a factory stock class, there were no single tweaks that produced huge reductions in lap times. It was a combination of many small optimizations that added up to make the kart faster than other karts. Chassis setup was a bigger single factor than any other. Center of gravity, corner weights, toe, camber, caster, frame and axle flex, if properly set, were some of the invisible elements that left rookie racers convinced that you were cheating in the motor. And so it is with Pinewood Derby. The sum of minor optimizations such as good wheels, well-polished axles, good lubrication, good alignment, maximum weight, optimized CG, and other unseen elements add up to produce a highly competitive car. It is not what you see that makes a fast car. It's what you don't see. If you found this video informative and useful, we invite you to give this video a like, and to subscribe to our channel for other Pinewood Derby and Rain Gutter Regatta episodes. Thank you. Disclaimer: the content of this video is for informational and entertainment purposes only. Derby Test Track was not sponsored by or affiliated with the manufacturers or retailers of any of the products tested or used in this video, or the Boy Scouts of America, at the time of testing or production of this video. All products used were purchased by Derby Test Track. Derby Test Track has made its best commercial effort to conduct all tests fairly and impartially. Your results could be different. The information provided in this video is believed to be accurate, however, do your own research to confirm its accuracy. Derby Test Track and the creator assume no responsibility for the accuracy of the information, injuries or damages resulting from the information provided or use of the products tested. Well done. You just put your iPad, TV or cell phone to good use, watching a video that was drier than the Atacama Desert, because you were curious, and took the initiative to improve your knowledge. Whether you aspire to be a future Elon Musk or Gwynne Shotwell, or present day or future good parent and mentor, we commend you and wish you success in your Pinewood Derby endeavors.